Okay, so welcome back. This is the last day of our workshop. This morning we are happy to have Conan Leung from CUHK, and he's going to talk about quantization of Kahler manifolds. So let's welcome.
All right, thank you very much for letting me to have this great opportunity to speak here. And soon. So this is a joint work with Wei Chen, Qin Li, Dan Wang, and Tony Yao, and supported by Hong Kong government. So these are the topics I'm going to speak about: deformation, quantization, just various quantizations, different scheme of quantizations. And at the end, we'll talk about Brane quantizations. I mainly will be discussing our recent work in the past 2-3 years with my collaborators on this. So let me very quickly remind ourselves that our setting is quantization on the symplectic manifold X, symplectic form omega. Typical example would be like R2 with a symplectic form dx dy, or you write as a C with symplectic form dc bar. Okay, and we are basically just studying quantum mechanics. It's okay, yeah. So we're studying basically quantum mechanics from a mathematical perspective. The main topics that we will be looking at from this perspective is deformation quantization and geometric quantization. Okay. Deformation quantizations, in short, is a non-commutative deformations of the function rings of the manifold X, okay? Meaning the following: if you have two functions f and g on X, and you change the product by adding some small changes, in fact h bar is just a formal parameter, to define a new product, and the main property is the product has to be associative. Okay? And another one is you want this operation to be local. So therefore, this term that you add to it should really depending on the at all those points up to infinite order. So this is should be some differential operator in both x and f and g variable. And the symplectic form come in as the leading order term of the changes of the commutative algebra to the non-commutative one. So the leading term of the non-commutative product is given by the Poisson bracket, which is essentially just the inverse of the symplectic form. So this is deformation quantizations. Geometric quantizations is associations of the manifold, and you give a vector space, Hilbert space called H. In a example, when X is a cotangent bundle of a manifold M, let's say M is just R, and there's a kind of symplectic form is just dx dy, X is just a variable in M. So in this particular case, the Hilbert space is just the L2 function on M. So in particular, you're only depending on half of the variable in X. Okay. In fact, if you look at it as a cotangent bundle of Rn, then a cotangent bundle you can write as a V plus V star, or you can write as V star plus V. So you can write as a cotangent bundle of V or cotangent bundle of V star. So therefore, you can also look at the Hilbert space as the L2 function on V star. So these are called the momentum quantizations. And then the relation between these two ways of describing it is called Fourier transform. As you will see very quickly, that we are going to discuss this type of Hilbert space depending on different way of obtaining a Hilbert space by different polarizations. So how do you do that in general instead of just cotangent bundle of M? So in general, if it's just a symplectic manifold, the way to obtain the Hilbert space involves two processes. Okay, well, take a look at here. In a cotangent bundle, first of all, it's some functions on X which depending only on half of the variable. And where does the symplectic form come in? In fact, the symplectic form is the curvature of some connection on a line bundle, which are called pre-quantum line bundle. So you require the symplectic form to be defined for integer so that you can have the line bundle with curvature equal to omega. All right, so you really should be looking at section of the line bundle L. Okay, in the earlier case, the line bundle is just trivial, even though the connection is not trivial. Okay, the second part is you have to have a way to cut off half of the variable. So this is what so-called polarizations, meaning that you inside the tangent bundle or the complexified tangent bundle, we choose a Lagrangian subbundle which are integrable. Okay, and then you require that those sections to be constant or less covariant constant along those directions, along P. Okay, or more generally, you can look at L to some power K. In fact, K should be very, very large. The relation with this formal variable H bar is roughly H bar is 1 over K. So K is large, H bar is very small. Okay. So these are some choices. Basically, once you have omega, then the line bundle is fixed. And then there are choices of polarization. As I mentioned earlier, you have a position and momentum polarization in the standard example. So this type of polarization are called real polarization. That means that the subbundle of tangent bundle, this polarization, is already defined over the real tangent space. Okay, so the complex polarization is really come from a real one complexified. So this is real. Okay, so these are called real polarization, just like the cotangent bundle example. Another one is that if the manifold is Kahler, in fact, you can look at the T01 because the complex structure really gives you a integrable Lagrangian subbundle. So this is another type of polarization. And this type of polarization is exactly the same as it has no real direction. So it intercept with its conjugate is completely zero. And this is exactly the same as saying that you have a Kahler structure. And so we call it Kahler polarization. So if it's not in these two extremes, then it's called mixed polarization. In a way that some part of it is real, some other part is not. Okay, some example of real polarization. You will see, we need to discuss some of that later. So the first example is cotangent bundle of a manifold M. And then you want, so as I said, the Hilbert space is just L2 function on the base. So you cut off all the y directions. So the polarization is all the direction generated by ddy. Another one which I study a lot in math literature is so-called a toric variety. So toric variety are symplectic manifold with the maximum amount of abelian symmetry. So they have a moment map mu. The image is a polytope which control all the symplectic geometry of the manifold. So therefore the manifold usually just write down this polytopes delta to say that this is a toric variety determined by this convex polytope in Rn. Okay, typical example is CP1, which is just the S2, and then the S1 action act by rotations. Okay, so you have the two fixed points, which is the north and south pole, and then the moment map is just the projections to the R. And then in this case, this is the polytope. This is just the interval, it's a polytope. And this is, you see that it's very much like the one before. And then the polarization is just this rotational directions. It's the direction generated by the S1 actions. Okay. However, this case, the polarization is singular. And singular is exactly along these 2 points because these are fixed points. So you don't have this, the S1 action does not generate a direction. So these are singular real polarizations. In fact, in general, it's very difficult to have real polarizations which are smooth everywhere. Okay. So in this case, the Hilbert space will be function depending on the half of the variable. So you think that uses the function depending on the base. However, because you're really looking at section along the which are constant along the fiber, and but the connection may not be trivial along this fiber. So to do that, you only have non-trivial flat section along this fiber if and only if these are integral lattice points. So therefore, the Hilbert space, in fact, consists of all those elements which are not smooth. So those are distributional sections. So, and then the support will be on the inverse image of some delta function type distribution in the inverse image of lattice point here. Okay. So these are our toric variety, which we'll need to discuss a bit later too. Okay. A more common polarization that we use all the time is the Kahler polarization, because we can find many examples of such in relation to a lot of other subjects like representation theory, algebraic geometry, and so on. So as I mentioned earlier, a Kahler polarization is the equivalent of saying that you can have complex structure so that the whole manifold is Kahler, and they're related by this. So once you have a complex structure, that you get a metric. Okay. And then in this case, you want to say that the function, instead of function, depending on z and z bar, and then you want it to be holomorphic, meaning they're independent of the z bar direction. So the polarization to cut off those direction is the z bar direction. So the Hilbert space, as I mentioned before, is just a space of all sections of L to some power, which are holomorphic. So these are just a holomorphic section of this Lie bundle as a standard object study in algebraic geometry. All right. So the complex polarization is like function in Z. Real polarization is like function in Y or function in X, and you can sometimes relate them. Okay? For example, you can look at a family of complex polarization depending on T. In this, if you do it like that on R2, when T go to infinity, the X1 will just go away. So this is a family of complex polarization at the end become a real polarization in a trivial example. How about mixed polarizations? Okay. Well, a typical example would be like this. Some part of it look like a real polarization, like X and Y, and the other part may be a Kahler polarization. This is a typical example. And how about others? Okay. So this is a joint work with my student, Dan Wang, who actually will be graduating very soon. Is here's some other way to construct mixed polarizations whenever you have some symmetry. Okay, so we are assuming that X is a Kahler manifold, but with a abelian symmetry by some torus. So T is acted by Kahler isometry with moment map. Okay, so it's not necessarily toric, just some torus action. So the idea is if it is toric variety, then you can have complex polarization and real polarization. But if you don't have a T action, then you can turn the T direction to a real polarization. So some part of it become real, basically. So explicitly, we can construct directly a mixed polarization, essentially saying that you turn the T action direction to be a real polarization. Okay. Again, just like toric case, some part of it is singular that we can describe very precisely. Okay, what about the Hilbert space? Okay, the Hilbert space will again be some distributional type object because just like toric case, it has to be distributional. So in this case, you can describe that any element in this. Yes.
Can I interpolate? So the mixed polarization, they are highly non-unique, right?
Just like complex polarization, you can choose a lot of complex polarization.
Yeah.
Or this one we consider explicit one. Just like if T is maximum in dimensions, like in the toric case, then you get in this case a mixed polarization, just a real polarization in that case.
Right. Do you have a way to parameterize all mixed polarizations?
No.
Like is it some kind of a cone? The set of all such things?
No, just like let's say in a complex polarization, these are all Kahler structure, not up to equivalences, right? So you still have a lot of infinite dimensional, right? In that case.
Oh.
Before you take the closure.
It's like infinite dimensional cone, I think, right?
Yeah. So let's just say a couple work here. So if we just look at maybe I use the other. Okay, if we just look at R2N, okay. So if a standard symplectic form, okay? And you can have a lot of complex polarization. Let's say just R2, okay. So the space of all complex polarization is parameterized by the unit disk as expected, right? So this is but because this is just given by SP2R over U1, okay? And then real polarization is parameterized by the boundary, which is U1 over O1.
Mm-hmm.
Okay? And then this way is really going to boundary. It's just exactly like X plus IY, and then sending T go to infinity, T go to infinity. So this is all. If it in a constant case, this is all the possible way of changing complex polarization, the real polarizations. Now, if you go to R4 instead of R2, so this is SP4R over U2. Now, this symmetric space, this is just Siegel-Harper space. If you look at the boundary, there are various boundary components corresponding to exactly Z1, Z2, that either one of them go to infinity, then that become mixed polarizations. If both of them go to infinity, that become real polarizations. Okay. So in a constant case, you can parameterize it like that. And this just corresponds to classical theory about compactification of symmetric spaces of tube type. Yeah. So in this case, this is just a generalization of what one expect in the toric case, meaning that we turn some of the group action direction to the real part. Okay, and then we can describe the mixed polarizations in this case. But in this case, because T is only some of the action, not the whole half-dimensional, so the quotient is not by points. In fact, the support of this polarization, the support of those sections will be some lattice point in the image of moment map. And then this are exactly corresponding to holomorphic section of the symplectic quotient for the corresponding lambda. Okay, so you can describe that in terms of symplectic quotient. In a way, a little bit like symmetry commutative reduction in some way. Another typical question that one look at in geometric quantization is you have many choices of polarization. As Conan was saying that, well, can you parameterize them? Well, I do not know, but at least there's a question about how dependent that this Hilbert space is on the polarization. A lot of work earlier on various aspects of this by like Esra, Witten, Hitchens, and Hamilton, Kono, and so on. Many people. And we look at one special case. This is not a very general case, but it's quite interesting related to what we had earlier. So continue to our last setting that we have a Kahler manifold with some torus isometry. Okay, so in this case, we have a complex polarization, and then we also construct a mixed polarization just a moment ago. As a matter of fact, we can have a whole family of complex polarization, beginning with the standard one, beginning with the Kahler polarization on this one. Okay, we have a family of Kahler polarization, so that the limiting one is the mixed polarization I just mentioned a moment ago. So you get a family of Kahler polarization, meaning you have a family of Kahler metric for this symplectic form. And this family of Kahler metric is in fact a complete geodesic in the space of Kahler metric in the Kahler form, like this Donaldson program type questions. Yeah. So in this case, explicitly, you can show that this is a complete geodesic. Yeah. And furthermore, I guess quite more interesting is at least when lambda is regular, so we described earlier that this mixed polarizations, these are distributional sections. In fact, you can exactly see how the whole thing happened is that if you look at the complex polarizations, because of the torus action, the complex polarization, the corresponding Hilbert space has the action by T, and you look at the lambda weight space. And then those sections will gradually concentrate and then near the mu inverse of lambda, and then concentrate to this distributional sections, yeah, in a more concise way. Okay. So these are similar to earlier work in the toric case, but we generalize to any torus action. And the proof is a bit different. We have to use more structure than, because in a toric case, everything is explicit. So in a general torus action case, you need to involve some other result in toric geometry. Not toric geometry, in Kahler geometry. So these are some examples. So we discussed a few aspects about deformation, quantization, and geometric quantization. Now, how are they related? These are related by the Berezin-Toeplitz quantizations. Okay. Well, let's just very quickly record the relation in the standard case. So let's just say R2. Okay. And then in this case, the line bundle is trivial, but then the connection is not. The metric is not trivial. Okay, the curvature is omega. So how is the relation between deformation and geometric quantization? So these are functions in X and Y. These are L2's function in X, but they are section of L. Okay. So how is the function in X, Y acting on function in X? Explicitly, the X itself act as a multiplication and Y act as a differentiation with respect to X. That's a standard example in the first thing we learn in quantum mechanics. Or if you look at, instead of R2, you look at a Z with a coordinate Z and Z bar, then the Z coordinate act as multiplication and Z bar act as DDZ. Okay, so in this action, in fact, you can look at it the following. So these are sections of L which are independent of Z bar. So this is really locally, you can write as a polynomial in Z, or maybe a power series in Z. And then they sit inside all the sections, which you can view it as all the function in Z and Z bar. Okay. So as a matter of fact, this way of writing the action, Z as multiplication, Z bar as the differentiations, can be described in the following way. You look at the function f, okay, you multiply with the holomorphic section. So now you become a section of L, but not holomorphic. And then you do the projection, orthogonal projection, back to the holomorphic sections. Okay, and these are called Toeplitz operator. So this is just add on this Hilbert space, okay, by multiplication by functions, but just smooth function. So you destroy holomorphicity and then do an orthogonal projection. Okay, so these are called Toeplitz operator. And in this standard case, this is exactly this one. Okay, and this slide I'm just showing you what type of calculation one use. It's just some integration, because you just say that, well, you multiply and then project it, that corresponds to some integration. So all you do is doing this type of integration. So you see that it's just like explicit integration. Then you prove that in the standard case, this particular way of action by deformation quantization and geometric quantization is just multiplication and projection, which are Toeplitz. How about general? Okay, so general, we just define this operator. Okay, so for just a general, let's say do a Kahler manifold. Okay, and then you do the same thing. You have a function f, and then you try to add on the space of a section of L. Okay, and then what you do is you multiply with the section with the functions. It's not holomorphic anymore. You do the orthogonal projection. Okay, you can do it for any large K too. Okay, so when K is getting bigger and bigger, it's more classical because K is going to be 1 over H bar. Okay, and these are called Toeplitz operator. But the main problem here is that this is not the R2N case, so this is no longer a associative product. Associativity is destroyed because you're doing orthogonal projection for general Kahler manifold. But this film, famous result that tells us that in the Kahler case, when K is large enough, this look more and more like associativity. So it says that if you compose these two for large K, so when K is larger and larger, the error is going to be smaller and smaller. So fix a particular power. This is you can think about this as h to the power j. Okay, fix a particular power to the power n, and then this one will look more and more like another Toeplitz operator. Okay, so once you do this, then even though each individual t to the power k is non-associative, but you can do it, have some asymptotic expansion of this behavior. It's like asymptotic associativity when for formal h bar, which is 1 over k. Okay? So you can extract a star operator, this non-commutative deformations, from this Toeplitz operator by letting k go to infinity. So these are called BT star product. Okay. So the next question is well, can one have a similar thing for real polarization instead of complex polarization? Okay. So first of all, I should tell you that in the Kahler case, this type of result, Kahler is being used in a very important way. Basically, what you really need is in the Kahler case, you always have two polarizations because P and P bar are not the same. So having this two transversal polarization is related to so-called DD bar lemma that we use in the proof in that result. So in a real polarization, to prove a corresponding result, we really need two polarizations which are transversal to each other. Okay. So it really very difficult to have real polarization which are smooth everywhere. If you have two of them, well, the manifold is essentially just a product of torus. At least if you require all the leaves are compact, because they are both integrable polarizations, so you can split the tangent space automatically, integrable. So therefore, the manifold essentially is just a product. Okay. Okay. So if we try to do an analog result, the first difficulty is the following. We try to do a Toeplitz operator, then we have to multiply and then project. But in a real polarization case, those are distributional sections. Doing orthogonal projections does not make sense. Okay, and as I mentioned, again, we need to use both polarizations, and then you have to suitably enlarge this real polarization to handle this projection of real polarization of distributional section issue. So the proof that we use, the main technique we use is micro-local analysis and some Fourier analysis. The proof is very different from the Kahler case. And this is a result with Yau, Tony Yau. So in this case, if you have, so in this case, you have a transversal real polarizations, and we can define the same type of Toeplitz operator. We can define, meaning that we have to enlarge the distributional section to be able to handle the orthogonal projection issue. And then prove the same type of asymptotic expansions of the Toeplitz operator. And then because of that, one obtain the star operator the same way. Okay. We can also, because I have two transversal polarizations, we can switch to the other polarization just by position and momentum polarizations. And then the two are related again by Fourier type transformations. Yeah. But how about singular real polarization, which you have many more, a lot more, like toric case. Okay, so in the toric case, it contains a C star to the power n. Now itself has two polarization. Okay, so they're transversal in the open part. Okay. So in this case, we can also prove a corresponding result because we have to analyze the behavior of the singularity more precisely at this case. Okay. So we can get a similar estimate and then use that to get a star product using transversal real polarization. So what is the main difficulty and how do we handle those problems in this case? Is the following. Okay. The first is let's say like a toric case, like in this case, the singularity is here. Okay, we first have to avoid the Hilbert space, those distributional sections, just rely on those places. So for that, we have to use a half form correction to move those Hilbert space to be a little bit away from this singular point. And then because those Toeplitz operator, when you do a projections, you have to have some, it's not that local, you have to cut off some of the places. So cut off a small label outside here. And then we look at those Fourier mode of those function f and g to only have finite Fourier mode. At least one of them has finite Fourier mode to avoid Fourier mode to be very frequent along those points. And then we can let epsilon go to 0 eventually. Okay, and that's where this epsilon coming in here. Okay, and but that is enough because when you get epsilon smaller and smaller, and then k get larger and larger, that is already enough to obtain this formal deformation condensation of star operator. Now, one can ask the next question is the following. Okay, so we have to come back to the Kahler case. Okay, so you have Toeplitz action, deformation condensation, and geometric condensation related by Toeplitz. Now we come back to the original case. How is that related to this standard example? Okay, in a standard example, this is just a multiplication and differentiation. It's just like that. Okay, at least when k is very large. So in order to do that, okay, we want to say that, well, if you localize this for large enough k, it to really be coming back to the standard example. Okay, so the way to then we attack this problem. So we look at each particular point. So look at one point, and then you want to keep on rescaling the point. And then once we scale the tangent space is this Cn. That's the thing that we want to look at. Okay, and then we have to try to rescale the thing, and then want to obtain this standard example in the limit. So how does this look like that one? Then how does a polynomial will look like the section? And then we have to use the peak section technique in the k coordinate, canonical coordinate, to approximate all those polymorphic functions, approximate this polynomial function of Cn. Okay. Now the main difficulty in this project is, well, you have to move with all the different k's. When you're moving, you have to compare with very different k, and if you change to a different k, those peak sections are not directly related to each other, which make the comparison very difficult. So we have to do a very elaborate scheme. I mean, this is canonical, but this is still elaborate. Is that you have to first look at for each. So you fix a point in x, and then try to do all these expansions in each order, and then for each order getting higher and higher order to get the approximation. And for each of those order, for L to the power k, you choose peak section around that point which look like z to some power. Okay, and then you choose that to approximate to some r. Okay, so this is once you pick the order of convergency, and then you look at all these sections which are related to each r. Okay, and then you have to quotient out the some equivalent relations. And then we argue that so it's quite complicated, but this is when you look at it carefully, this is the obvious way to do it after you see it. So you can recover this by that this is a kind of expansion of all the possible sections at that point, and then you can argue that that is just like the polynomial of z. And the main thing that you need to prove is this is the right thing is that if you look at a particular f functions, you look at all the Toeplitz operator for different k, okay, and then that can be take a limit, okay, because of this particular process to this Hilbert space, okay, formal Hilbert space. Okay, and this is our theorem with Caldwell and Chinley that doing this function, the Toeplitz operator can take a limit which acting on this Hilbert space, and then they really get a Toeplitz this deformation quantization. Okay, and then this is really the Berezin-Toeplitz quantization. Okay, and this is local and irreducible and everything we expect, and this is really recover the standard example. So now we come back to a round. So at each point, you can get this deformation quantization acting on the geometric quantization. Can you globalize it to get a shift version? Okay. So we want to globally to get this structure. So this has to really use a different approach. Okay. So the globalized one is using this Fedosov approach in the deformation quantization. But our Fedosov approach is a bit different. First of all, we are restricted to the Kahler case. However, we use this Fedosov approach in the Kahler case. The result is better than the symplectic case. Okay? And the approach we'll get the two advantage, for example, is we can prove the one loop acceptance on the co-chain level, as you will see later. And also we can use this to study non-formal, obtain result on non-formal quantizations. And all this will not work if you just do this Fedosov type in the symplectic case. Okay. So quickly recall what is the Fedosov quantization is the following. If you have a smooth function, it's about deformation quantization. We are just seeing how to deform the product of the functions. All right. So just if you take a smooth function, you try to localize at a point. You take a Taylor expansion at one point, but you want to globalize it. So you have to take a Taylor expansion on all possible points. So you look at the Taylor expansion at a point C, then the coefficient also depending on C. Okay. So if you look at all this data for each C, the Taylor expansion is really a formal power series. So this is really a symmetric power of the tangent space, cotangent space. This is when I say head, this means formal symmetric power. So this is at each point you get a Taylor expansion, and this is called a section of the Yau bundle. So therefore, from a function, you associate to a Taylor expansion at each point C. Okay, this is a section of the Yau bundle, but this is really coming from the same function f. So therefore, if you differentiate with respect to C, this is 0. But now you see that when you differentiate that, if you differentiate the C here, you can differentiate the C there. And so you get some relation between differentiate C and then relation to this A, but you shifted this by n to n minus 1. And so therefore, this relation here saying that the section really comes from the smooth function is related to the differentiation of that, this term. And then this operation, we just switching form part to switching this one to the form part. Okay. So this relation is saying that if a section satisfies that, that really come from Taylor expansion of a smooth function at all various points. Okay. So this is the same as this is in the kernel of the D. This is what happened when the space is just R. If the space is not R, then the curvature has to come in. So you have to keep on modifying this by all the derivative of the curvature. Okay, and so this is the result that the smooth function you can describe as Taylor expansion on all the possible points which are related by the kernel of a flat connection. Okay, so that is the Fedosov perspective. Okay, so to do it explicitly is the following. First of all, you look at the real Weyl bundle. Again, this just means that you look at the Taylor expansion at every possible point. Okay, so this is the Weyl bundle. But then instead of just that, we also want to look at differential forms. Okay, so this is a form part. And so you get the exterior power and the symmetric power. And you can look at switching one of these back and forth. These are called the delta and delta star, which is the operator as I mentioned here. Okay. All right. So these are just switching one of these the Taylor expansion back to one form part. Okay. And then if you forget all these Taylor expansion part, just the original form part, this is called a simple map. Okay. So this is a real case. In the complex case, okay, you can complexify the bundle. Now you can look at those which are 1-0 type or 0-1 type. So you look at form which are holomorphic part or anti-holomorphic part. Okay. So this is like all the PQ form, and this is a P0 form and CUHK form, kind of like that. But this is on the symmetric power instead of exterior power. So this is the Weyl bundle and so on. Okay. So we do the same thing as I was saying that. Let's start with X. So these are all, you can think about this Taylor expansion of all the functions. Okay, so therefore on each fiber, this is all this function. And then because now this is on each fiber is a linear space, so you can get this standard star product on this R2N because the manifold is symplectic. Okay, and as I mentioned earlier, that we try to construct a function. We try to construct a connection here of this form. Okay, and the connection of this form together with some correction by some power of the exterior derivative of the curvature, and this is this operation I here, and more precisely is given by this. Anyway, it's just the curvature, and then keep on differentiating n-2 times, and then you suitably look at it as an element inside this Weyl algebra. Okay, so this is the connection we define. Okay. And the statement is the following: if you restrict the connection to just the holomorphic part, this connection was defined by Krapanov. These are called the L infinity structure in the Kahler manifold case. So when you restrict to the holomorphic part, this one is flat, and also the flat section is exactly the holomorphic functions. Okay, and what we did is to quantize these questions to really look at this connection, divide this connection on all of this, and then again, this is a flat connections, and this connection, this flatness conditions is the same as this Fedosov equations, and then the flat section is exactly the Taylor expansion of all the smooth functions. Okay, this is the important part. So smooth function corresponding with flat section here. Now, because the curvature coming, this relation is quite complicated. So this flat sections can be related to this function in this way, which can be solved inductively once you start with F. Okay, but in a complicated way. Once you do that, then because the fiber-wise, this W now have a and also because this connection preserve the star product fiber-wise. Okay, and so therefore you can fiber-wise look at the star product. Okay, and then move it back. They come because it's still flat, so therefore it comes from a function, and then that function is the star product of F and G. This is a very nice product. Because of time, let me just skip that one. Okay, and quickly let me say that what we was doing a moment ago is really like local quantum observable. Okay, there's a BV quantization to obtain so-called global quantum observable by solving a quantum master equations, and that is really what one needs to construct the correlation function that the physical quantity. So the usual deformation quantization is not really the one for the physical term. So our work, part of the work is really how to solve this quantum master equations by solving this Feynman diagram argument. Okay, and we prove that a one-loop extent that this is where we use this Kahler property in a very important way. Okay, and then once you solve the global quantum observable, and then we can compute the combination functions, and then we will cover this algebraic index field, okay, where this is the correlation function. So this is a physical quantity that one look at. Okay. And let's see. Okay. So I do not have much time here. So let me just very quickly mention that. So what we just did a moment ago is the deformation quantization of Fedosov approach. In fact, we can try to do a geometric quantization in this way, which was not discussed in Fedosov perspective. So the deformation quantization is doing this flat connection here. Now, if you try to do the same thing for the geometric quantization part, okay, and then try to get this product. And the problem is this is no longer a flat connection. That's the trouble because the curvature here is something with a two form, which if you took a bracket, that will be gone. But if it's not the bracket part, then this is not trivial. And then that's why you have to twist it by a formal line bundle to make this a flat bundle. Okay, and so we can do that. Okay, so roughly speaking, as this Fedosov approach, we can extend it, include the geometric quantization part. But the problem is this is a formal line bundle. Okay, and you can still talk about the flat section and so on. Okay, and then this is how we globalize this construction that we a moment ago construct earlier. Okay, let me skip this non-formal deformations. Yeah. Okay. So the last thing that I want to say is the Brane quantizations. Now this is really a two-dimensional sigma model, also called the A model, instead of what we had earlier as quantum mechanics. Okay, and because we are two-dimensional, we have boundary conditions, and traditional theory boundary conditions of higher category, which are Lagrangians and Hermitian line bundle. Okay, but Kapustin and Orlov says that in fact you can also include coisotropic A brane, and the main difficulty is to understand what is the morphism between two coisotropic A brane. Okay, for this symplectic structure omega. Okay. Typical example of coisotropic A brane is the following. When the symplectic manifold is underlying a hyperkähler manifold, where the symplectic form is one of the Kähler form, okay, then the total space is a coisotropic A brane, and it's no longer flat. The curvature is omega j here. It's not this omega k, it's omega j. Okay. So, and then this is called BCC. And then you can also look at BCC bar where the curvature is minus of that. Okay. So the thing that we try to understand is for this symplectic form. But as a matter of fact, in this case, this brane is a brane, meaning Lagrangian brane, A brane for the symplectic geometry for this omega k. But at the same time, this is A brane for omega I and B brane for j. So this are called ABA brane. Okay. Now, the question is, how do you define the morphism space for coisotropic A brane? Okay. Now, it's because this is ABA brane for the B model, okay, which are just complex geometry. It's easy to define. Okay, but there's no guarantee that this is the same morphism space between that. Okay. So this is studied by Gukov and written that it tells us that this type of B model, okay, is related to like deformation quantization and geometric quantization in various way. Okay, and then from physical discussion study, if the space is X, one would expect that this coisotropic A brane, in this case, the morphism space can be described in terms of a complex structure. So this is in this case, of course, this is well defined because this is just complex geometry. Okay. And then one will try to use that to study the representation field. Now, what we did with Conan Leung is the following. Okay. Now we are in the case that this BCC bar. Okay. So both of them are space filling, so coisotropic A brane. Okay. And in fact, you have a whole S2 family. Okay. So these are a twisted family, okay, of generalized Kähler structure. And what we show is, in fact, this whole family has a symmetry, okay, the SP1 symmetry. Okay. So in particular, the symmetry will tell us that if you look at it from the J complex structure, which is something that we can define, okay, and the symmetry will tell us that you can relate to the symplectic form, which is something that we cannot define earlier. Yeah. But the main thing, this is different from many of the earlier work on this similar direction, is this particular case, the curvature of L of this coisotropic A-brane is not preserved by the SP1 action, unlike all the previous situations. Okay, so that's the main differences. So we can look at this for some other setting for the SP1 symmetry, and then look at the corresponding morphism space. And the last one, that one is trying to understand, which is still the most important one, is how about we look at BCC and some Lagrangian brane. Okay, so that is a future project. Okay.